All right, welcome to Chapter 8. In our first section of Chapter 8, we're going to be using logs to solve exponential equations. So now we're actually going to be able to solve these exponentials using our logs, something we kind of came close to last chapter, but not quite. So just a quick recap, in this chapter we'll continue learning more about logs. Let's recap what you know. So there are 3 bullet points right here. Take a moment and please answer those 3 questions. All right, so what is a log and how can we convert it to another form? Remember, the log is the inverse of an exponential function, and we can convert logs to exponentials and vice versa, so exponentials to logs, using the circle dance method or the Bay method, whichever method you prefer. Then it says, what do you know about the log key on your calculator? Remember, that is a base of 10. And then draw a quick sketch of the graph y equals log of x, and then write it in log in the graphing equation with the h and k. So remember, our log graphs always are the inverse of an exponential, so we have an asymptote on the y-axis. It's going to start close to the y-axis, always cross through 1, 0, and then grow slowly. And then our equation with the h and k in it, y equals a times log base b of x minus h, and then plus k. All right, so now it says r log base 2 of x and y equals log of 2 to the x equivalent. Prove your work graphically and algebraically. So it says use your knowledge of log graphs to make a sketch of y equals log base 2 of x. Then use the graphing calculator or Desmos to graph y equals log of 2 to the x. Sketch the graph below. So log base 2 of x, remember, is going to be similar to what we just had there. It's going to cross through at 1, 0. It's going to have an asymptote on the y-axis, be really close to it, and then grow slowly, but it does grow a little faster than the other bases. It's one of the fastest growing bases. And now if we graph log of 2 to the x, remember that would be a base of 10. So that we'll label this y equals log base 2 of x. And now I'll graph log of 2 to the x power. And when I graph that, I get a straight line. Again, that's a very, it's not a steep slope. It's almost like rise 1 over 3 maybe. And then I'll graph that or label that as y equals log of 2 to the x. So we can see that they are not equivalent to each other. Log y equals log base 2 of x is not equivalent to y equals log of 2 to the x power. The other way we can do it is now convert y equals log of 2 to the x and y equals log base 2 of x and y equals log of 2 to the x into exponential form. So here is where we would use our circle dance. And if I do that, I would get 2 to the y equals x. And if I do the other one, log of 2 to the x equals y. Remember, this would be a base of 10. So I would have 10 to the y equals 2 to the x. And those are, again, not equivalent. So basically, so r y equals log base 2 of x and y equals log base 2 of x and y equals log of 2 to the x equivalent? No. And we just use counter examples to show that. We used the graphs were not different was one way we showed the counter examples that they weren't equivalent, and then we converted them for our second way. And so here it says, for the log statements below, convert the exponential form to see if the following equations are equivalent. So for these, we're going to convert, because it does say convert. All right, so I'll write log base 5 of 25 equals y. And when I convert that, I get 5 to the y equals 25. And for that to be a true statement, y would be 2, right? 5 squared is 25. For the next one, log base 25 of 5 equals y, I would have 25 to the y equals 5. And for that to be true, here y would have to equal 2, and here y would have to be 1/2 though, because it would be the square root. So these are not equivalent. I look at the next one. Again, it'd be log base 10 of 2x equals y. And when I convert that, I would have 10 to the y equals 2x. And for the next one, log base 2 of x equals y. And when I convert that, I'd have 2 to the y equals x. And you can see, nope, the bases are different. That would not be equivalent either. All right, now we're going to use the graph to see if these other two work. So for our first one, we're doing log of x squared. And the squared is inside, the x and the squared are inside the parentheses of the log. And then we're doing log of x all squared. The whole thing is squared after that. And when I press graph for that, ooh, that's our first one. There's our second. So we can see that, nope, they are not equivalent. We can make a quick sketch. The first one goes down like that. And the second one is just a tiny graph, so not equivalent. And then for our second one, or sorry, our fourth one, letter D, we have log of 7 to the x power, and then x log of 7. And believe it or not, this one only shows one graph because, looking at the table, all these y values are the same. So these actually are equivalent to each other. So we made a sketch. And our sketch looks like a straight line. There's only one of them, so they are equivalent. So on the previous page, we saw that letter D was true. This is called the power property of logs. In the power property of logs, if you notice what was true here, we had log of 7 to the x, and that was the same as the x in front of the log. So we kind of have the same thing. We had a log, same base. We had the 7 in parentheses, but here the x was in the exponent, and now the x was moved in front and multiplied, and that's equivalent. So if we look at this, log base b of a to the x, the exponent is going to be in front and then multiplied by whatever it means, x times log base b of a. So it says, do you remember seeing a problem such as 1.04 to the x equals 2 in your homework? What methods did you use to solve for x? So before, when we had a problem where x was in the exponent, we had to use problems such as guessing and checking, or solutions or strategies such as guess and check, or solving graphically. Now, however, we can solve this equation algebraically with the help of this power property of logs. And so we have 1.04 to the x equals 2. What I can now do is, once that base and the x and the exponent are isolated, I can now take the log of both sides. So the way you're going to undo an x in the exponent is to take the log of both sides, kind of like to undo a multiplication, you divide. To undo division, you multiply. To undo addition, you subtract. To undo a square, you square root. To undo an x in the exponent, we're going to take the log. And now we can use that power property. That x was in the exponent. We can move that x in front and multiply it now by whatever remains. So I can rewrite this now as log of x. I can rewrite this as x times log of 1.04 equals log of 2. And so now it's a regular multiplication problem. To get the x by itself, these are separated by multiplication. So to get the x by itself, I'm going to divide by log of 1.04. So to get your answer, you're just going to take your calculator and type log of 2 and divide it by log of 1.04. And again, this would be log base 10, and you could really do log of any base. It's just that log base 10 is the easiest to type in your calculator. So our answer is going to be 17.67, we'll say 3. If I double check my work, if I did 1.04 to the answer, second answer, notice I get 2 exactly. So it says we will use the undoing strategy to solve when x is in the exponent. So remember, undoing is PEMDAS backwards. So if I look at this example, first thing I'm going to do is undo addition, subtraction. So I have subtraction here. So I'm going to add 9. And that would give me 120. Then I'm going to undo multiplication and division. So there's multiplication right here. So I'm going to divide by 5. And so that would give me 3 to the x equals 24. And now, this is the new part. Before I didn't know how to solve this, but now all I have to do is take the log of each side. So if I take log of 3 to the x and log of the right side, log of 24, I can then rewrite this left side with the power property by moving that x in front. X times log of 3. Again, that would still equal log of 24. And now this is a multiplication problem. So to undo multiplication, I'm going to divide. So divide by log of 3. And I am left with log of 24. So I'm going to type in my calculator. Log of 24 divided by log of 3. And I would get 2.8928. I like to keep 4 decimal places if possible here. And I just rounded 1, 2, 3, and I rounded this 7 to an 8 because of the 8 being above 5. All right, try doing these 4 on your own. I'll go over a couple of them shortly. All right, for number 2, for number 1, you would just take the log of both sides right away. For number 2, I would have to undo addition subtraction first. So I'm going to subtract 8. And then I'm going to divide by 2 because I'm undoing multiplication division next. So I'd have 5 to the x equals 136 divided by 2, which is 68. And then I would need to take the log of both sides. Because when I take the log of both sides, that x is now going to be moved in front of my log out of the exponent. And now it's a simple multiplication problem, so to undo multiplication, I divide. So I'm going to divide both sides by log of 5. And so I would type in my calculator, log of 68. Make sure you close the parentheses, divide by log of 5. And I would get 2.6217. Careful with number 3. There is not an x in the exponent. Okay, so remember, if this was a 2 in the exponent, you take the square root. If it was a 3, you take the cube root. So ultimately here, you're going to need to take the 8th root. Okay, so be careful with that one. You're only doing logs when there's an x in the exponent. And then for number 4, there is no addition subtraction undo, so I'm going to divide by 2 first. And so that will give me 8 to the x equals 128 divided by 2 is 64. Now, although you could use logs here, this is kind of common sense. 8 to the what power is 64. So here I'm just going to say, all right, that's 2. If you wanted to use logs, you could go ahead and have done that as well. All right. Hopefully you enjoyed this. Have a good day.